Tonight, we're diving into a story that's all about brute strength meeting incredible intelligence. It's a story about how to bend one of the toughest materials on Earth, not with more force, but with a single, perfect, calculated thought.
I mean, think about it. It's a huge challenge for our most advanced industries. When you're building something like a jet engine or a custom medical implant, good enough just doesn't cut it. It has to be absolutely perfect. So how do you even get there?
Because the future of manufacturing isn't about hitting harder, it's about thinking smarter. Okay, let's get into this.
First things first, we have to understand the material at the very heart of this puzzle. Because, this isn't just any old metal, it's a modern marvel.
Say hello to titanium grade 5. This stuff is a true supermaterial. It has a staggering tensile strength, which is really just a fancy way of saying it's incredibly, incredibly hard to pull apart. But the amazing part is that it's also remarkably light. This combo makes it the absolute gold standard for parts that cannot, under any circumstances, fail.
And this slide just lays out the problem perfectly. The old-school way of shaping metal, stamping it between these massive custom-made dies, that works great if you're making, a million of the exact same thing. But for aerospace or custom implants, you need one-of-a-kind parts. And for that, traditional stamping is just impossibly slow and way too expensive.
So, engineers obviously needed a new approach. They needed a more flexible, a more intelligent way of shaping this supermaterial on demand.
And that brings us to this, Single Point Incremental Forming, or SPIF for short. Now, instead of one massive stomp, SPIF is this really clever dialless process. It uses a small computer-guided tool to kind of gently and gradually, sculpt the metal into a complex shape.
So here's how it actually works. You take a sheet of titanium and lock it into place. Then, this little rounded tool starts moving along a very precise, computer-designed path, making thousands of tiny, localized pushes. Bit by bit, this intricate 3D shape just sort of emerges. It's an elegant process for sure, but it's also incredibly sensitive.
And this is where our mystery really begins. Because getting SPIF right isn't just about flipping a switch. It's about finding a secret, perfect recipe.
You see, there are 3 key dials you can turn: how fast the tool spins, how deep it pushes with each little pass, and how fast it moves across the sheet. And these 3 inputs control the 2 things that matter most: getting the steepest possible angle on the part's wall without it breaking, and getting the smoothest possible surface.
But here's the real kicker. These variables are all tangled up together. You tweak the speed, and maybe the surface becomes smooth as glass, but the whole part could fracture under the stress. It's this razor's edge balancing act with literally thousands of possible combinations, and the stakes are unbelievably high.
I mean, that's the multi-million-dollar question, right? You could spend months, maybe even years, running physical tests, wasting tons of super expensive titanium just trying to find that one perfect recipe. There had to be a better way.
So instead of going down that path of endless trial and error, the researchers brought in a modern kind of detective. They decided to train a digital brain to find the answer for them.
And that brain is an artificial neural network, or ANN. The simplest way to think about it is as a computer model that learns from experience, pretty much just like our own brains do. By showing it examples, it can start to understand these incredibly complex relationships and then predict what's going to happen next. So here's the genius move. They ran just 20 physical experiments using different settings. They carefully measured the results from each one, the wall angle, the surface roughness, and fed all that data to the ANN. The AI just chewed on that data, learned all the hidden patterns, and built a predictive model. It essentially taught itself the complex physics of the whole process without ever touching a single piece of metal.
So after all that training, it was time for the moment of truth. Have the digital brain actually cracked the code? Well, the results were nothing short of astonishing. Just take a second and look at that number, 0.99999.
That is what's called an R value. It's an accuracy score. A score of 1 means it's a perfect prediction. The AI got so close to 1, it is statistically almost flawless. It had learned to predict the perfect wall angle with absolutely breathtaking accuracy.
And that wasn't just a one-trick pony. Remember that second critical goal, the surface smoothness?
Well, there you go again, another incredible score. The AI had mastered both sides of this puzzle. It could predict the 2 competing outcomes with near-perfect reliability. This meant it could now run thousands of virtual experiments in just seconds.
And this is what it found. The single best combination of settings to get maximum strength with minimum flaws. A spindle speed of 200 RPM, a teeny tiny incremental depth of 0.1 millimeters, and a feed rate of 2,000 millimeters per minute. The researchers then ran one last physical test using this exact recipe, and it confirmed the AI's prediction perfectly.
Okay, so what does this all really mean? This isn't just some cool lab experiment. This is a real glimpse into the future of how we make things.
The impact is huge. This is a fundamental shift from slow, expensive physical guesswork to intelligent, predictive manufacturing. Think about it. Less waste, faster innovation, and higher quality parts for the industries that rely on perfection. It's like giving our best engineers a digital co-pilot that can see all the hidden patterns and find solutions a human might never stumble upon. And that really leaves us with a final thought to chew on. We just watched an AI master the art of shaping one of the world's toughest metals. What other incredibly complex challenges are out there just waiting to be perfected if we just teach a machine how to find the answer?